In this part of physics, we are going to talk about two main points: simple harmonic motion and also waves. In simple harmonic motion, we are going to talk about Hooke's law, which is related to spring, and also we will talk about simple pendulum. For waves, we're going to talk about types of waves and speed, frequency related to waves, and also standing waves and waves of sound. Okay, for the first point now, which is simple harmonic motion. What is simple harmonic motion? So this is the first point now. Simple harmonic motion, what does it mean? Simple harmonic motion, it is the motion that the force or the restoring force of it is related or proportional to the displacement. How does that happen? It happens in two things. So it happens on pendulums, and also it happens with what? With the springs. For example, now when I have here a spring, this is spring now. When I try to put here a weight, and this weight will take it down. So the restoring force, now there is a force in the spring that will try to get the spring back to its place. So the amount of force here, that is the restoring force, which is the force responsible to restore the spring to its original length, this restoring force, its amount is related to the displacement. So the more the displacement, the more that this one will be extended, the more the spring will be extended. So that means the more the force will be. So that means this one now is type of simple harmonic motion. So simple harmonic motion is any motion that the force or the restoring force of it will be proportional to the extension or to the displacement. For the pendulum, it's the same. Here we have a pendulum, and this pendulum now, as we know, it moves as oscillations left and right. So that means this here, point A, for example, and here point B, and here point C. So it will keep moving from A, B, C, then C, B, A again. So now when it goes here now, from here to here, that means it is now extended. This is displacement now, displacement from here to here. Now, this displacement, this amount of displacement is a factor for the force that the force will be responsible for restoring it back. So that means the force or the restoring force in this example also is related or proportional to the extension or the displacement. So this one is also another type of simple harmonic motion. So simple harmonic motion in general is related to the force, or where the force in that system is proportional to the displacement. The restoring force is related to the displacement. Okay, here now we are going to study these two examples are examples of what? Of simple harmonic motion. Simple harmonic motion. Okay, for simple harmonic motion, here you have two examples. On the right, this is the spring, and on the left is what? Is the pendulum. Okay, we're going to start by this one now, which is the spring. For the spring here, as we know, there are many types of springs. One spring, you're going to find it very light and it's very easy for you to extend it, like as the spring of the pen. It's very light and it's easy for you to spring it or to compress it. And we have very tough springs, like the springs of the cars next to the tires, or the springs of the cranes. So that means it's very hard to be compressed or expanded. So based on the manufacturing or the way it was manufactured, there is a constant for the spring. What is this constant now of the spring? So that means those who produced the spring, based on the material, they know how long it can be extended and how many newtons as a force, what amount of force can extend it for 1 meter. So that means the amount of force that can extend this spring for 1 meter is called what? The constant of the spring. So what is the constant of the spring? It's the amount of force that will be able to extend this spring for 1 meter. Who identify that, or who put that limit? It is the manufacturing company based on the materials and based on the experiments. So that means it depends from one spring to another. One spring you need maybe 1 Newton, 2 Newtons to extend it for 1 meter. And other springs, maybe you need hundreds, thousands of Newtons to extend it for 1 meter. So what is now the main formula now? The main formula, if we change the formula here, we're gonna see that the force, which is the restoring force, after you take the spring down, the restoring force, it's gonna be, as you know, we make it negative because it's restoring force. The force that is stored, and it's gonna be, that means it is in the opposite side of the main force. So the weight will be here, and the restoring force, then it will take it up. So that means it's in the opposite side, so you write it negative. So it equals the constant of the spring times the distance. And this 1 meter is what? Times the distance of extension. And this is what is known as Hooke's law. So what is Hooke's law? F equals K times X. What is K? Is the constant of the spring, and X is the extension, for how long it was extended. If it extended from here to here, 2 meters or 1 meter, that means you put this extension, even if it is very small, like 3 centimeters, you put it in the unit of meter, then you put it here to find the force or the restoring force in the springs. And we use the springs to know the weight of many things, and we use it in many I think in all the vehicles it's used, and in other machines. Okay, for the spring now, we need to know that the spring is just one example of simple harmonic motion, and this is its formula. And also it has another formula, that is energy. What is the potential energy that will be stored in the spring? And it will be restoring energy here. It is restored in its place. It will equal half kx squared. So that means you have 2 main equations. These the equations that are related to the spring, and we understand now the spring and its constant and its 2 formulas. This formula is the same. This formula is the same, just it was rearranged as F to be the subject. So here 2 main formulas for the spring, and we understand the spring, the extension, and the constant of the spring, and that's all for the spring. Any other questions comes, then we apply these formulas to solve them. Okay, we go back now to the left side, which is pendulum. For the pendulum now, the pendulum goes from A to B, and now when it goes from A to B and comes back, we call this one the time or the period of the pendulum. The period, that means the time it takes. Okay, this time now it equals 2 pi times the square root of L over G. What is L? L is the length of the wire of the pendulum, and G is the gravity. So as we know here now, since just here, this one is in the denominator and here in the numerator, so that means the relationship now between T, the time, and gravity is inversely. Is what? Inversely. So that means time and square root of G, the relationship between them is what? Inversely proportional. What does that mean? That means the greater the gravity, the smaller the time, or the shorter the time it takes to make one oscillation. Okay, again, for example, now I have one pendulum here, and this pendulum on Earth, and I have another pendulum on the moon. As we know, the gravity of Earth is greater than the gravity of what? Of the moon. So in this case now, if it is the same pendulum on Earth and on the moon, where it will take more time, or where it will take longer period to make one oscillation? Of course, on the moon, it will take more time. Why? Because in the moon, less gravity. When it is less gravity now, as we said, less gravity, that means the relationship between time and gravity is inversely proportional. So less gravity, that means more time. Greater gravity, that means less time. So that means on Earth, higher gravity, so that means less time, less period. So now we understand what is pendulum here, and it is used in general in many things. And one of the uses of pendulum is to find the gravity of Earth. So if you take just a pendulum and you take a timer and you see how much time it takes one oscillation, and you put the time here and you take the length here, and you know what is 2 pi. So that means what would be variable is just what the gravity, which is g. So you solve as math to find what the gravity of Earth. And we understand now that the time, which is the period it takes, is directly proportional with the length and inversely proportional with the gravity. So the higher the gravity, the less the period, which is the time. And related to the length, the greater the length of the pendulum, the greater the time it takes to make one oscillation. So you understand now what is springs and the formulas related, and you understand pendulum and the formulas related, and the relationship between directly and inversely, direct and inverse proportionality. Okay, we go now to the next point, which is waves. We finished now simple harmonic motion briefly, and we go now into waves. What are waves? Or what is waves? Waves is a disturbance in a medium. This is wave. Okay, what type of waves, or how many waves there? Okay, light, when it comes from the sun to the earth, it comes through waves. Sound, when you hear it now, it comes to your ear through waves. Water, when it moves, this is waves. When you shake a rope and it moves, the wave moves, this is a wave. Okay, how many types of waves, or how can we classify waves? How can we classify what? Waves. Okay, waves can be classified if we classify them based on the medium. It moves, so we're gonna classify them into mechanical and what? Electromagnetic. Mechanical waves are the waves that they need medium to travel through. Like sound now, when I'm talking to a person next to me and he hears what I'm talking, that means there is a medium between me and him, which is air particles. So this medium now will travel or will transfer the waves to his ear. So that means in this case, we call this type of waves mechanical waves, since it needs medium. Water waves, when you throw something into the water and the waves spread around that point, these waves, they have a medium, which is water particles. So these ones also are called mechanical waves. Okay, what about electromagnetic waves? Electromagnetic waves, like the waves that come from the sun, which is light, which is visible light, and radio waves, microwaves, gamma waves. These waves that they go, or they are transferred through the electromagnetic spectrum from the sun. They don't need medium to travel through, so we call them what? Electromagnetic waves. So based on the medium, we can classify them as mechanical and electromagnetic. And also we can classify waves based on their movement, how their movement. For example, now if you have a rope here, and your hand is here, this is your hand, and you shake your hand up and down. You shake your hand as fast as possible up and down. You're gonna see that the rope is moving what? This way. Okay, as you see, the force that you are exerting, it goes up and down, while the wave mainly, they go what? To the right. So that means in this case, the angle between the force that is the cause of the wave and the direction of the wave is perpendicular. So these ones, we call them transverse waves. We call them what? Transverse waves. Okay, another type of waves is like sound. So if this is now your mouth and you produce here sound, the sound will go this direction. So that means in this case, when you punch it here, so the direction of the force, that is the cause of the waves, and the direction of the waves are in the same line, in the same direction. So those ones, we call them what? Longitudinal waves. Longitudinal waves. If you have waves that are both transverse and longitudinal waves, these ones we call them what? Like the water. So when you throw something inside the water, you're going to see that there are waves like circles, they go around it, and these ones, they go up and down. So that means they go up and down in one direction, and also they go what? Up and down one dimension, and they go in the other dimension. So that means they are longitudinal and transverse at the same time. These ones, we call them what? Surface waves. We call them surface waves. So based on the movement here, how they move, we have three types of waves. Okay, another classification here, we can classify them based on the direction. So if we classify them based on the direction, we have one dimension, and you have two dimensions, and you have what? Three-dimension waves. One-dimension waves is like the rope. It will go, as you see the rope here, it goes into one direction, into X direction. So that means this is one-dimensional wave. And two-dimensional is like the water. The water here, when you throw something in it, the waves go up and down, and also so vertically up and down it goes. It has movement vertically, and also it have movement horizontally. As circles, it goes around that point. So it has two dimensions here. So we call it like water. And we have three dimensions waves like sound. When I'm talking now, my sound, it doesn't go only into one direction. No, the person who is in front of me can hear me. The person who is on my back also, he can hear me. The person who is in my right, also the person who is on my left. So that means that means the sound waves can go into three dimensions. So we say that sound waves is an example of what? Of three-dimensional waves. So you understand now types of waves and how they are, what's their classification. In general, when we draw a wave, we take, this is y and this is x. This is y and this is x-axis. So that means the wave go this way. And the distance between this point and this point, we call it what? One wavelength. One wavelength. And the distance from here to here, we call it what? Amplitude. Amplitude is the distance between the main axis of the wave and the furthest point of the wave. And this point, we call it crest, and this point, we call it what? Through. So this one, we call it crest, and here through, and here amplitude, and this one is what? Wavelength. Okay, any wave now, it has a wavelength, and it has a frequency, and it has a speed. Okay, or velocity, how these ones are related to each other. Okay, as we know, the speed in general, it equals distance over time. Distance over time. So for the wave, the speed is the distance. But here the distance, we use wavelength as the distance. We use what? Wavelength as a distance. So then it's going to be the wavelength over time. This is now the speed of the wave. That means how many wavelengths per time, per second. Now, what is frequency and what is time? What is period of the waves? Frequency, it means how many rotations this wave can make per second. So how many rotations per second? Number of rotations per 1 second. So this is now frequency. Frequency in too many types of waves. Even the light waves, it has frequency, and each color, red, blue, white, yellow, each color of these colors, it has a specific frequency. And frequency means how many wavelengths, how many circulations rotations the wave can make per 1 second. Okay, what is the time, which is the period? The period that this wave takes is exactly the inverse of the frequency. And also the frequency is the inverse of the what? Of the time. Okay, what's the difference here between frequency and time? We can understand by this example. If a wavelength can make 2 rotations per second, 2 rotations per 1 second. In this case, what is the frequency? The frequency, as we said, how many rotations per second? How many rotations here? 2 rotations per second. So that means we say the frequency is what? Is 2 hertz. Is 2 hertz. Now, what is the time? The time now, it means how much time one rotation takes. One rotation takes. And time, as we know, is the inverse of what? A frequency. So 1 over f. So that means the time now is going to be 1 over 2, which is what? Half. What does the half mean now? It means half second. So that means now one rotation, it will take half a second. So the time or the period, it means per one circulation, per 1 rotation, how much time it takes. But the frequency, it means per 1 second. Per 1 second, how many rotations? So that means they are inverse of each other. So since the t equals here 1 over f, and also f equals 1 over t, equals 1 over what? T. Okay, if we now reshape this formula, what will we get now? We get that the speed equals lambda over time. Lambda, we're going to change it over time. We're going to change it to be 1 over time. So now this 1 over time is f, which is the frequency. So that means the speed now on the speed of the wave, it's going to be wavelength times the frequency. So this is now a common formula. To find the speed of any wave, you multiply the wavelength of that wave times its frequency. Okay, now, in general here, the relationship between the speed and the frequency is directly proportional, here directly proportional, but the wave and the wavelength and the frequency, they are inversely proportional. So the greater the frequency, the less the wavelength, or the greater the wavelength, less the frequency. So we understand now wave and types of waves. We understand how to find the speed of wave. What is the main formula here, or 2 or 3 formulas to find the frequency and to find the period and also to find the speed of the wave. Okay, we have another type of waves also. It's called what? Standing waves. What are standing waves? So on guitar, for example, or lute, which one of the most musical instruments, when you press this string of the guitar, the string is fixed here in 2 points. So the string now, when you press it down, it goes down, then it goes up, then down goes up. So that means it's still moving like this. So that means this one as example of wave, which is called what? Standing waves. Standing waves. Standing waves are the waves that are or that look stationary. That look stationary. That means when we see them like what? As stationary waves. And guitar and lutes, just examples of what? Of these standing waves. In standing waves, here, these 2 points, we call them nodes. We call them what? Nodes. And here also nodes. So that means here is node and here is node. And this part, we call it what? Antinodes. Antinode. So on the nodes, that means the amplitude is 0, but here the amplitude is the maximum. So that means we have nodes and we have what? Antinodes. Nodes is as points where the waves meet, but the space where they have a space between them, we call it what? Antinodes. Okay, for echo, which is the speed of sound now. If we're going to find the speed of sound, as we said, we use the previous formula to find the speed of any wave. But for sound, if you are here and you produce a sound and the sound goes into a wall and comes back, then you're going to hear your sound again as echo. In this case, just you have to put in your mind the distance here will be twice. The distance of going there and the distance of coming back. So that means if I say the distance between the person and the wall is 100 meters. And when you this person, when he produces a sound, he heard the sound after 10 seconds. After 10 seconds, he heard. What is the speed of the sound? What is the speed of the sound? Again, a person produces a sound and he heard this sound after 10 seconds. If the distance between the person and the wall is 100 meters, what is the speed of the sound? So the speed of the sound, as we know, any speed equals distance over what? Over time. So here now, the speed equals the distance. Do we calculate distance as 1 meter? No, we calculate the distance of moving there, and then the distance to be back. Because now you heard it after these waves waved, after these waves traveled into the wall, then came back to yourself. In this case, that means it traveled to a distance of 1 meter. So that means here you write it 200 meters over what the time it took. That means 10 seconds. So that means 0, 0. That means it's going to be what? 20. So that means these waves now are traveling 20 meters per second. So that means it took 10 seconds to go and to come back. So that means to go only takes 5 seconds. 5 seconds, which is 100 meters in 5 seconds. That means also what? 20. So we understand now briefly simple harmonic motion and also waves. And we have other questions. You can solve them that are related to these ideas and formulas. Thank you.